Here's a problem in rigid body kinetics. We're looking at a roller and it's going to be rolling down a ramp, and part of the problem statement is that it will roll without slipping. What we want to determine is how long is it going to take to reach the bottom of the ramp and how fast is it going to be going when it gets there. We need to know something about the ramp geometry. The ramp angle is 30 degrees, and when we go from the upper position to where we contact with the flat part at the bottom, that's going to be a height difference of 3 meters. And so because of the 30-degree angle, we can calculate that the distance that is going to be traveled by the center of mass of the roller is going to be 6 meters exactly. We need to know something about the roller. It's made out of steel, and because of the geometry with the cuts there, it would be very difficult to find the mass moment of inertia by hand, but SolidWorks can do that for us very easily. Again, the material is steel, and you can see 7,800 kilograms per cubic meter was the density, and so the mass of this roller is about 40 kilograms, and the moment of inertia about an axis through the center of gravity is 0.2398 kilogram meter squared. That's the axis that it's going to be rolling about. And we also need to know what the radius of that roller is, and it's 100 millimeters. So let's draw a free body diagram of the roller, and we've shown the x-axis as being down the ramp and the y-axis perpendicular to that. So the forces acting on the roller include its weight, normal force between the roller and the ramp, and also a friction force that causes the roller to roll. And so we can apply our equations of motion here. In the x direction, we have a component of weight and the friction force, and again setting the sum of those equal to the mass times the acceleration of the center of gravity in the x direction. No acceleration in the y direction, so we can have the normal force and a component of weight as well. And for the sum of the moments, we can do it one of two ways. We can either take the sum of the moments about an axis through the center of gravity, center of mass rather, which we know the value of that, or we can take the sum of the moments about point O. And because of the fact that this is rolling without slipping, we know that point O is an instant center, has a velocity of 0, and so we can do this. We can say that the sum of the moments about that point is equal to the moment of inertia about an axis through that point times alpha. So if we look at these equations, it looks like we have four unknowns. We've got the normal force, the friction force, acceleration in the x direction, and the angular acceleration. So a lot of problem statements we might be given the coefficient of friction, but we're not in this case. But what we are told is that the roller will roll without slipping. So what that means is that there's a relationship between the acceleration of the center of mass and the angular acceleration. Also, of course, there's a similar relationship between the velocity of the center of mass and the angular velocity. So with that in mind, there are really only three unknowns here. But because of the fact we're looking at this last one, the sum of the moments about point O, I don't have to know what the friction force and the normal force are. I can simply solve that one and find out what alpha is. And if I can find out what alpha is, then because of this relationship here, I can also know what the acceleration is in the x direction, which is what I need to know to figure how long it's going to take to get to the bottom. So here's the equation that we need. Again, what I need is the moment of inertia about that point O on the perimeter of the roller. And so for that, I have to use the parallel axis theorem. I know the moment of inertia through the centroid, or through the center of mass. I got that off of SolidWorks, the 0.2398 kilogram meter squared, and what I have to add is the mass times the distance squared. The distance between the two axes is the radius, 0.1 meter, and so that gives me a moment of inertia through about an axis that passes through point O of 0.6397 kilogram meter squared. And so now I know everything in that top equation except for alpha. So plugging in values for the weight, I've got the mass times g, 9.81 meters per second squared, times the sine of of theta, theta is 30 degrees, and the radius is a tenth of a meter, or again 100 millimeters, or a tenth of a meter. And on the right side of the equation, we have this value we just came up with for the moment of inertia, I sub 0, and that's times alpha. So we can solve for alpha, 30.66 radians per second squared. And again, knowing the relationship between alpha and the acceleration in the x direction, we find that the acceleration in the x direction is a little over 3 meters per second squared. And that's a constant acceleration. So we can integrate that once with respect to time to get the velocity, and the initial velocity is equal to 0, so we just simply have the acceleration times time for the velocity. And to find the distance traveled, we integrate one more time. Again, velocity initial is equal to 0, and we're measuring everything relative to the starting position, so x naught is equal to 0, and so we're left with the x being the acceleration over 2 times time squared. And from that we can figure out how long it's going to take to travel the 6 meters from the top to the bottom. Solving that for t is just slightly less than 2 seconds. So that was one of the things we were trying to find. The other thing is how fast is it going when we get to the bottom. Again, that's simply equal to the acceleration times time. Plug in the time value we just found, and we find 6.07 meters per second is the predicted volume. Excuse me, the predicted velocity at the bottom of the ramp. Okay, let's go to the SolidWorks simulation here, and we'll run this. And to make sure that this was going to roll without slipping, we have to put in a coefficient of friction, and I put in a relatively high coefficient of friction, 0.5. Now I think that's going to be high enough. Let's take a look at the velocity here for just a moment. And it looks like our assumption was correct because our numbers match up pretty well. Let me do this to the axis so we can get that a little better. And you can see, yeah, just shade under 2 seconds to reach the bottom, and right about 6 meters per second, slightly more than that when we hit down at the bottom of the ramp. Now, another way I can tell that this didn't slip is by showing what we call a trace path. So let me zoom in a little bit here. And a trace path is simply a curve that traces, as the name implies, traces the path of a single point. So there's a single point on the perimeter here, this point right here, that as it rolls down, you can see it becomes the point of contact here, and as we roll, then this is the path that it's following. And because of the fact that when it comes into contact, it makes a sharp cusp like that, we can determine that the velocity at that point, at that particular time, is equal to 0. So it does roll without slipping. For contrast, let's look what happens if we pick a much lower value of the coefficient of friction. I put in a coefficient of friction of 0.1 for this. Now, it's kind of hard to tell. I mean, you can tell it's definitely rolling, but is it slipping as well? Again, looking at the trace path, it looks very much different than with the higher value of friction there. You can see that where the point is in contact with the ramp, that we don't get that sharp cusp there. What's happening, of course, is that we are rolling and sliding at the same time. And if we look at the velocity profile, as we might expect, it's going to get to the bottom faster, and it's going to have a higher speed when we get to the bottom of about 7 meters per second. And again, the other extreme case is if we look at it with no friction at all. And in this case, you can tell that we're pure sliding and not rolling at all. So we would get the same solution here. Really, we're treating this as a particle when we do that. And so there's our maximum value of speed that we can have is looks like it's about 7.5, 7.6 meters per second. Okay, let's go back to our calculations for a moment. We just, again, predicted the velocity of 6.07 meters per second at the bottom of the ramp. In addition to do it with the equations of motion, we could also use conservation of energy here. Now the reason we can do that, even though there is friction, is we remember if rolling without slipping, the friction force is not doing any work. And so we don't have to consider that in our calculations here. So at the top, we have a kinetic energy equal to 0 because we're starting from rest. And if we define the datum as the position we're going to be at the bottom, then mgh, with h being the distance above the datum, or 3 meters, is going to be our potential energy. And at the bottom, the potential energy will be 0. With the kinetic energy, remember that if we were using a particle here, it would just be 1/2 mv squared. But because of the fact that we have a rigid body, we have to include the rotational energy as well. So 1/2 mass moment of inertia times omega squared has to be considered as well. So if we equate the energy at the top with the energy at the bottom and plug in our known values, again, it looks like we have two unknowns with the velocity and omega, but remember there is that relationship between the velocity and omega. The velocity is equal to r times omega, or omega is equal to the velocity divided by r, is how we've shown this here, since we're trying to find for the solve for the velocity. So the left side of the equation, mgh, and the right side, 1/2 mv squared plus 1/2 I omega squared. And again, for omega, we've put in the velocity divided by the radius. And so solving this, we come up with the same velocity that we got by using the equations of motion, 6.07 meters per second is our answer. We're going to continue looking at this problem in a couple of additional videos. In the next one, again, we just kind of guessed at a coefficient of friction and found out that we didn't slip with that high value coefficient of friction. So how would we determine what coefficient of friction is required to prevent slipping? And how do we calculate the speed at the bottom if we do have a combination of rolling and slipping? We'll do that in the part 2. And in part 3, we'll look at the 4 rollers that are shown here. 2 of them are steel, 2 of them are plastic, 2 of them are solid, 2 of them have the same geometry of the one we just looked at. And we'll ask the question, which one of these is going to get to the bottom first? Does mass make a difference? Does geometry make a difference? We'll figure that out in part 3.